Okie dokie, everybody. This is 7-1 day 2. Today, when we look at linear and nonlinear systems, we are going to take a look at how we use systems of equations to model and solve real-life problems. So we know there's lots of different things that we can use these for. So we're just going to highlight a few of them and just to kind of get you thinking about some applications that you might use a system of equations to solve. All right, so some applications. One thing we're going to talk about is we're going to look at cost of producing items. So if we're doing a production and we're making a bunch of manufacturing something, how much does it cost to manufacture them? And then also look at when do we start making profit, looking at some of these economic ideas and looking at something called breaking even. So what does it mean if you break even? So before we kind of launch into the equations and everything, I want you to think about, pause the video for a second. What do you think breaking even means? Just as an idea, if you break even, and then what do you think it would mean in terms of looking at costs and looking at your revenue or amount of money you make? What would break even mean? So pause the video and take a moment to think on that. All right, so just some of the basic ideas, and then we'll talk about what that break even means. Maybe it matched up with what you said or what you were thinking. So total cost of producing, and then we're just going to say X units, so X standing for the number of units of your product, usually has two different main components. So think about what would go into producing something. There's going to be some sort of initial cost or startup cost, and then there's going to be some sort of like cost per unit, right? So we have a certain amount of money that's just going to happen every time we produce something. So initial cost could be things like, I'll just kind of brainstorm for a second, think on your own, what could be an initial cost? Setting up the machinery, buying the machinery you need, getting a space to produce it, hiring people to work there, whatever it might be. So you've got some startup costs, but then also you have those, I need to buy materials every time I make one or whatever it is. So we call that the cost per unit. So there's kind of two things that go into, usually there's can be other things too. I suppose you have research and development and things like that. But what do you think break even would mean then if we're producing something? The break even point, what would that correspond to in terms of the cost and the revenue curves? Well, it would be when the cost is equal to the revenue. In other words, the amount of money that we had to spend to produce the items is equal to the money that we bring in. Revenue is the amount that you bring in when you sell it. So it's when they're equal. So if that's the same or equal, what place on the graph would that be? Well, if that's where they are the same or it's shared, that is their point of intersection. So we're looking for that same thing that we were talking about in day 1. We're looking for where these two graphs are the same. So that point of intersection. Now, when we look at a lot of situations, they could be linear, but again, they wouldn't have to be nonlinear. So we think about those point of intersections in any kind of situation. So break-even analysis can also be approached from the point of view of profit. So your profit is the amount of money that you make above and beyond your cost. So if we think about what profit would look like, so I'm going to use P for profit, your profit is going to be whatever your revenue is, the amount of money you take in total, like when you sell all your items, minus whatever cost you had to like produce those. So the startup cost and the cost per item. So we're looking for profit, right? We want to maximize our profits. We want that number, that P, to get really big. In other words, the bigger the revenue gets, the better off we'll be. Now, the break-even point then, if we're looking at it from the point of view of profit, would be when the profit is 0. So when we have no profit at all, that, another way of saying that then is like the revenue would be equal to the cost. So again, getting back to that break even. So if R minus C were 0, in other words, the profit was nothing, that's when you're breaking even. So I have it sort of laid out in your additional notes, just in words, if that's an easier way for you to kind of think about it. So total cost, first of all, so total cost, cost per unit times the number of units. So that would be some kind of calculation that we'd have to make, whatever that cost per unit is, times however many units we're making, and then whatever the startup cost was. And then the total revenue, remember, is going to be how do we figure out the price per unit, whatever that is, times the number of units. So the price per unit would be something that we would like, how much are we going to charge for it? 15 bucks, 20 bucks, whatever that might be. So those are kind of particular to the situation that we're looking at. All right, so let's take a look at an example. We're just going to do a pretty basic one with pretty easy cost and revenue function. So let's take a look and kind of highlight some of the big information here. It says the cost of producing X units, so they're using X for the number of units again. So this is cost, is 1.5 times X plus 1,500. So that's the cost function. So 1.5 times X plus 15,000. So what does that mean? What are all those numbers telling you? Well, if X is the number of units, this 1.5 then is going to be, let's look back at our model, the cost per unit, like how much does it cost to be able to make that item? So cost per unit. So taking a look at that equation, that'd be $1.50. So whether that's materials, electricity, whatever it is to produce that. The 15,000 then, what would the 15,000 be? That would be the initial cost, like the startup cost. So that might be buying the machinery to produce it, whatever it is. So those are the initial, like the startup costs. Sometimes they say that. So we have our cost function. All right, then what's our other function? The revenue that we get for obtaining or selling those X units is 5X. So that's the revenue function. Again, that's a linear equation, 5 times X. What does that 5 represent? That number up front. Let's take a peek at our revenue function. That's the price per unit. So that's how much we're charging. So that's the price per unit. So we're charging $5 a piece. So that's the revenue we bring in. That's not the profit. Remember, that's the revenue. So we still have to subtract off our cost to see how much profit we actually get, but that's the revenue or the money that we take in. All right, so what do they want us to figure out here? How many items, remember kind of our annotating here, underline what we're looking for. How many items should be sold to break even? Remember, break even is finding that point of intersection, the solution to the system. So the point of intersection is what we're looking at. So we have to figure out what's the best way to solve this system of equations. All right, so I'm going to have you pause the video and take a moment to think about what method do you think we should use to best solve this system. All right, well, we talked about a lot of different choices in day one to be able to do that. Because this one is set up so nicely, like one is kind of solved for if we're thinking about, remember, when revenue is equal to the cost, we want to see when these are the same. We're really just saying that the cost function better be equal to the revenue function, right? When we're thinking about the different ways we're talking about that. So the revenue has to be equal to the cost. So I think the easiest way for me to take a look at this would be just solving this equation when they are equal. That's our break-even point. And since they're both written in terms of number of units sold, that X is the same, we just have to solve for X. So variables on both sides. So go ahead, pause the video, solve the equation for X, and see how many units we need to sell to break even. All right, so let's take a look at our solving. So I subtracted, divided, and I get 4,285.7. Now, if you are doing a report and you need precision and you want that, that exact amount, you could probably say that. But in real life, we're not going to produce a 0.7 of something. Nobody wants to buy 0.7 of a product. That's not really a great deal. So probably going to round just to say how many units sold. So the number of units that we would need to sell, number of units sold to break even would have to be, I would say, 4,286 units. You could also figure out what that revenue or cost would be if that happened. So if I wanted to substitute that 4,008 or 286 back into either of those equations, remember it's a solution to both, so it's a point of intersection, we could actually figure out what approximately that either cost or revenue would be. Now, they didn't specifically ask us to do that, but we certainly could. All right, what's another way that we could solve this? Thinking about what we did in day one. So that we kind of did a substitution, or sort of we set the equations equal because we knew they had to be equal to break even. Could we also do this in a graphing approach? So let's take a look. What if we put in those two equations and decided to solve by graphing? So let's see if we could figure out what that would look like. So plus 15,000, see if that gave me the right number of zeros. Yep, and then 5x for my y2. And I'm just going to go ahead now. The issue that we're going to have when you graph is you're going to see the 5x one, that 1.5 plus 15,000, you're not really going to see. So our issue when we're graphing these is going to be, it's probably going to be way off of the -10 to 10, because just think about what we just got, like 4,000 something. So you will kind of have to mess around with your window a little bit. I'm going to show you what I used. I did 0 to 5,000. Now, again, if you were doing this just as a method, you wouldn't know that the answer was 4,200. So you might have to play around, do a zoom fit, try to see if you can see the graph a little bit better. And then I was guesstimating the revenue is like 5 times whatever that is. So 5 times 4 something. So I went up to 30,000 just to be able to see it. So that's kind of what I came up with for that. So now we can actually see the point of intersection. So I can do my second calculate, and I want to intersect. So then it says, hey, is that my first curve? Sure. Is that other one my second curve? Sorry, I have to keep going up and down. Yes. And then guess I can get her close. Oh my goodness, that's going to take a long time to get there. Yay. So I got it close, and then I'm going to press enter, and then we can see what those values are. So there's our 4285.7, which we rounded to 4286, and then there's what our revenue / cost when they are equal to each other would be 21,428.57. So 21,429 approximately. So we have that. So again, they didn't ask us for that, but we could figure out that cost / revenue when we could figure out when that was. So as soon as our revenue exceeds, that would be something else maybe that would be interesting for people to know. As soon as our revenue exceeds $21,429, we're turning a profit. So we would know when that's happening, and that's how many units we'd have to sell, so to break even. So it's a really quick and easy calculation by solving a system. And again, you could support it graphically, although when those numbers are big like that, actually algebraically is way faster and way easier to deal with. All right, so we're going to do one more example of breaking even. Looking at 2 different kinds of sales. So representing and looking at how 2 different things are performing compared to each other. So instead of looking at just one item, we're going to look at 2 and compare them with each other. So this is in your additional notes just for another example. So we have 2 movies, an animated and a horror film, are released in the same week. In the first 8 weeks, the weekly ticket sales, so S for sales, in millions of dollars, decreased for the animated movie. So they started off and then they're going down. And they increased for the horror movie. So those revenues were going up. So what we're looking for is, when did the 2 break even? In other words, when were they earning the same amount of money? So breaking even means that their revenues were equal to each other. So they were earning the same amount. So breaking even. Now, take a look at the 2 equations and think about which one is which. So can you tell which one is the horror film and which one is the animated by the equations? Think about what each of them are doing. Pause the video and see if you can jot that down. All right, so which one is decreasing? Which one is the value going down? Well, look for the one that's subtracting. That must be the animated then, because that one said it is decreasing each week. And so the one that is being added, its revenue is going up, must be the horror film. So the sales for the first one must be the animated. And notice the starting sales for the animated was more, 108 million. And then for the horror film, in its first week, it was only 16 million, but then it increased from there, 9 million per, time is in weeks. So X = 1 represents the first week. So it increased 9 million every week. And then the horror animated film is decreasing 94 million per week. All right, so let's see when they're going to break even. And obviously this can't continue for either one of these infinitely. You can kind of think about why we can't. I mean, at some point they're just going to go down to 0, or you can't keep growing forever and ever and ever. I mean, the movies aren't going to keep selling, but for the short term, we can look at that analysis, and they're both linear currently. And so we're assuming that that linear would continue. So in what week will the ticket sales be equal? So again, equal, we're going to set these 2 equal to one another, and we're going to solve. So we're looking for when their revenue is the same. All right. So go ahead, solve for X, see how many weeks it takes to make their sales equal. All right, I think I need to get one more decimal point in here too before we keep going any further. That was supposed to be 9.4, 94 million, just to decreasing like quite a bit as I was looking back at it. It should be 9.4, so sorry about that. make sure that you get that in there. We'll have to just adjust our place value then. So your answer might be a little bit different. So make sure you double check that. So it's losing 9.4 million a week, not 94 million a week. Otherwise it'd be down to zero pretty quick. All right, so when you look at your solving, I moved the added 9.4 to the other side, subtracted the 16, divide by the 18.4 then. So just make that adjustment and you'd end up with x equals 5. What does that mean? Time in weeks then, it would take 5 weeks for the ticket sales to be equal. So 5 weeks for the ticket sales to be equal. And then again, we could figure out, to be equal. So we could figure out what that sales amount would be just by plugging that 5 back into either of those equations for the x if we wanted to. So we could figure out how much that was earned in sales. It's a pretty quick calculation, so we could figure that out as well. So we could do our 16 and 45, which would be 61 million. So there'd be 61 million in sales when they were equal. And then one would continue to grow and the other one would continue to decline. So after 5 weeks, the horror film would be making more, and then before 5 weeks, the animated film was actually making more. So lots of cool things you can do with systems of equations. All right, so that's just kind of a little bit of a taste of what you can do with systems in terms of real life application. We'll be looking a lot more as the chapter goes on.